Hello, hello. Welcome back to the great outdoors where we do code. This time we're looking at the UTXO implementation of the payment processor. And so let's dive right in. Once again, we've got our accounts. This is our payment processor, Alice Jing, the normal stuff with our public key, private key, and address. And this time we have our initial state. Our initial state includes an airdrop to the payment processor. So instead of minting any coins, we're just giving them all to the payment processor in the very beginning. But let's take a look at the unsigned transaction. So this is kind of very alien and kind of complicated looking, but what we're doing in this first transaction is we're taking this 1,000 and we're sending it to 3 different addresses. We're sending it to Jing, to Alice, and back to the payment processor, right? 250, 250, and 500. So the payment processor, in reality, is sending 250 to Jing, 250 to Alice, and keeping 500 for themselves. So now the second transaction is actually Jing and Alice pooling their money together to send their money back to the payment processor. So, for some reason they didn't like those coins and they just wanted to send them right back. So let's take a look at our state object. And so at time 0, this is after our first transaction was applied, we see that we have our first output, right? This is the one that was included in our initial state. This is an object. It has an owner and it has a value, right? $1,000. And the owner is our payment processor. And then it has 3 more outputs, right? And these outputs include the 250 to Jing, the 250 to Alice, and the 500 back at the payment processor. And so you can see A2, right? It matches A2. And you'll notice that our list of UTXOs, right? This is our is spent list. We see that there's a 1 for the first one because we consumed this first output to create these 3 new outputs, and there are 3 unspent outputs after that. So this is the state object after applying our first transaction. Now, after applying our second transaction, we've just increased the number of outputs. We have all of the outputs that we had before, but we've got this new one, an output back in the to the payment processor. This is when Jing and Alice pooled their money together to send it back to the payment processor. So now all of these are spent and these 2 are unspent. And then we're just catching a couple errors at the end. So that is essentially what our state is doing. Let's take a look at how this actually gets done. So the state object, right, we're creating it. We have our initial state, and then we're applying our transactions just like before. But the real difference is, what does our apply transaction function look like? Because we are doing this kind of UTXO model, it's a little bit more complicated. So first, what we're going to do is we're going to recover a list of signers. So notice that our first transaction only had 1 signer, but our second transaction actually had 2, right? There were 2 inputs, and those inputs were owned by 2 different people. And so if you look at this signed transactions list, we can notice that there's first the unsigned transaction number 1, there's just 1 signature. But for unsigned transaction number 2, there were 2 signatures. Jing and Alice were both agreeing to send their money to the payment processor. In our UTXO video, we saw that Jing and Alice they were sending their money to the Build a Better Future Foundation. So now, in this apply transaction function, first we're going to recover all of the signers, and then we're going to add them into a list. Next, we're going to loop over all of our inputs, and we're going to grab them out of our state object by their index, right? So we have a long list of inputs, and we're sending the input index. So if you look at our transaction number 2, we say that output at index 1 and output at index 2. Those are our 2 inputs. And so we're going to grab them from our state object, and we're going to then check that the signer is included in our list of signatures. So remember, each one of these inputs has an owner, and we want to make sure that it is included in our list of signers. And that basically says, okay, if your transaction references 2 addresses, make sure that both of those addresses are signing that transaction. Otherwise, it's not going to go through, right? We're missing a signature for some particular input. Next, we're going to look at our state object and we're going to make sure that they are all unspent. So remember, if it's not equal to 0, that means it's not equal to unspent, which means that we're trying to spend a spent output. Don't want to do that. Say that 5 times fast. Now, the next thing is we're going to, after we've done these 2 checks, we made sure that the owner is included and that the input is unspent, right? So these are our inputs. We're making sure that all of our inputs are valid. Then we're going to add it to our total input value, because remember, our rule is that we want to make sure that the input value equals the output value. Next, we're going to say let the total output value equal to 0. And we're going to iterate over all of the outputs, and we're just going to add up their values. And we're going to make sure that they are equal. This is very simple, just input equals output in terms of value. We are not able to mint any coins. Next, we're going to update the state object. This is all of the checks that we needed to do. We just needed to say, are all the signatures provided? Are all of the outputs unspent that we're trying to use? And are the input values equal to the output values? Once we've made those 3 checks, that's enough to say, let's add these outputs to our list of outputs. Now, what we're going to do is first we're going to set the inputs to spent. So we're going to check grab the input index, and we're just going to set it equal to 1, right? You don't want to spend the same output twice. Next, we're going to just add the outputs to our list of transaction outputs, right? We're just iterating over all of them, and we're going to add those to our list. And we're going to push a new 0, which means it is unspent, to our list of is spent. We're calling it UTXOs here. Maybe that's a bad variable name. Now, and then we're going to return the state. Remember, once again, this is JavaScript. It's returning a pointer to the state object that we've mutated in this function, unfortunately. Not a pure function. Now, that's about it. We're going to also check some errors, but in terms of normal functioning, that's all really we need to do. First, we're going to try an invalid signature. Once again, this is the payment processor is signing something that Jing should have been signing, and we're going to show that that actually fails. If you look here in our output, we caught the error. Great, good stuff. And then lastly, we're going to try replaying the transaction, and that will fail as well. Note that the replay of the transaction does not require a nonce. Why does it not require a nonce? Well, it doesn't require a nonce because in the UTXO model, there is a rule which says every output can only be consumed 1 time. That means that the whole property of replay protection in terms of, using this nonce to make sure that each transaction can be consumed only 1 time, that we don't have to worry about, because it's like if we had a rule which said you can only send from 1 address once in our account model, then we wouldn't need the nonce. But because you're able to reference the same account multiple times, then we need this kind of nonce stuff. But, there are different trade-offs. We had a little bit more of a complicated apply transaction function, but actually in terms of lines of code, we're doing pretty good. We've got, 84 lines of code, and that, or even, even less, what is this? How many lines of code is that? Like 30 lines of code to do this apply transaction, and it was relatively easy. So this is, yet another cool way to implement a payment processor. This is the code that lives on each one of the nodes in our network, right? So each Ethereum node, for instance, is running the transactions and applying them at all times. And, that goes for Bitcoin, that goes for every blockchain there that at least has full nodes. Not every blockchain these days does. And so this is the code that sits on each one of our computers. And this code needs to be performant enough to, run on a laptop and whatnot. But anyway, we're going to go over all of that in Chapter 2. I'm looking forward to, talking to you soon and going over the networks and then get into consensus algorithms. Oh my God, this stuff will be fun. So until next time, talk to you soon. Bye-bye.